Assalamu alaikum, dear students. Welcome to lecture number 6 of week 3 of Geotechnical Engineering 1. Today we are going to discuss about clay mineralogy, that is various mineral forms of clay soil. Okay. Last time we discussed various types of soils based on the classification, starting with gravel as the largest size, then followed by sands, which is the smaller in size than the gravel, and then silt, which will pass through sieve number 200. They are small as well, and then microscopic and submicroscopic flaky clays. Okay, so we already discussed in detail about sand, gravels, and silt. And we discussed that they are basically formed by mechanical weathering of their parent rock, because they are inert, they don't carry any charge, so they have no affinity towards water, so they are not plastic, okay, and they cannot be molded in shapes, and their strength is more than the clay. Clays, however, we said that we will discuss them later. Clays are basically result of chemical weathering of their parent rock, which means that the parent rock is to be chemically weathered, chemically changed into the material, forming clay soil. Okay, because of this chemical weathering, the clays by various chemical weathering process will result into various different types. You see, many times you see clays, they have different colors as well, like over here you can see a glacial oceanic clay, which is darker in color, obviously because of the water effect. Then you have bentonite, which is usually used in the drilling as a drilling fluid, drilling mud. It is a buff color, which you can see. Then you have kaolin clay, which is whitish in color, or space white kaolin, sometimes known as well, commonly used in pottery, making the pots the more ornamental type of the pots, which we usually find in the market. And then we have fresh green clay as well, which you can see over here. So they may be in different colors, and you may see they have various kind of issues as well. Majority of the time the issues with the clays are they are susceptible to high volume changes, because they can absorb a lot of water, and then when somehow if dry season comes, they can give up a lot of water as well, and then it can form basically a lot of cracks in this as well, because of the changes in volume. Okay, which is usually not ideal for the structures, because if you are putting a foundation in such soil that has a volume changes, then because of that you can have non-uniform settlements in the building, which is usually harmful. Okay, but however, clay is commonly used. We come across clay, we even make those houses with the clay as well in villages, which you can still come across those old construction, they were made of clay. So clay is commonly used in various engineering activities. Previously they were used for construction of houses. Nowadays they are used as a filler material in the roads. They are also used in the construction of bricks. Clays are also used in the clay core of the dam for prevention of moisture transfer, because of their very less moisture transferability. Their permeability is less. So there are a lot of properties of the clay that needs understanding. So that's why we will discuss various types over here. So to understand how the different types of clays are different from each other, we need to understand the clay formation, clay minerals, how they basically are formed. Clay minerals are basically complex aluminum silicate structure, which is usually consisting of two basic building units. Okay, silica tetrahedron or silica sheet, which you can see over here in this color, and alumina octahedron or gibbsite sheet, which you can see over here. So any clay mineral will have those two sheets, but in different combinations, which you can see over here. Okay, so typically they will have those two sheets in different arrangements. One will be tetrahedral silica sheet and another will be octahedral gibbsite sheet. Okay, in different combinations they will be formed. If they are in different combination, they can basically form a different clay mineral. Okay, so commonly, because of the combination in which the silica and gibbsite sheet exists, there are basically three types of clays. Okay, that includes kaolinite, which has got something like this kind of structure. Okay, the thickness of one sheet is about 7 angstrom, which you can see over here, 7.2, but we roughly consider it to be 7 angstrom. Okay, and similarly then we have illite, which got this kind of structure. Okay, so the structure of the atoms, the molecules is like this, and the thickness of the single structure building block is 10 angstrom over here, which you can see over here, which is called illite. Okay, this is illite, this is kaolinite, this is illite, which has got potassium atom in between as well. Okay, and then we have Montmorillite, which is this kind of structure. Okay, silica sheet, gibbsite sheet, silica sheet, and then inside there is water, and then again another unit. Okay, so the difference is over here. Okay, over here you can see the gibbsite sheet is directly connected to silica sheet. Here the silica sheet is connected to another silica sheet through potassium atom, and over here silica sheet is connected to silica sheet, but there is water in the middle, and the size is also different of single building block. Okay, so I know we are going into much more into mineralogy and chemistry of things, but it is very important for engineers to understand, because later on we will be dealing with these three distinct types of the clays, and they will exhibit different types of properties. So then you should be clear that why a particular type of clay is giving you a particular kind of response, okay, with respect to construction. So if you want to visually define them or visually identify, you can identify kaolin very easily. Okay, the previous thing which I mentioned, there was at atomic level, at molecular level. So obviously you will not have electron microscope with you all the time, so you can basically check the molecular structure. Neither you will have the techniques like XRD, XRF analysis, which are basically used to do those kind of jobs. So visually kaolin is lighter in color, okay, which you can see over here. It's white or sometimes whitish off-white in color. Then you will have illite, that will be slightly grayish in color, okay, and then you will have Montmorillite, which will be usually darker color of a clay. Okay, so darker to buff colors, then they will be commonly as distinguished as Montmorillite. Okay, but there can be different colors depending on the areas in which the clay is basically formed. So over here we will look at this animation, which will help you even further clear the things, how they are basically formed, the various mineral forms of a clay, and how this silica and gibbsite sheets, they come together and form these various types of the clays, okay, at the atomic level. Okay, so almost all clay minerals are made of two fundamental sheets, as we discussed, and these sheets are basically tied together, okay, by negative and positive bond. Okay, negative attract positive, we know that from your knowledge. So one is tetrahedral sheet or silica sheet, okay, or silica tetrahedral sheet, and another is gibbsite sheet, which is octahedral sheet, or alumina or gibbsite sheet. Okay, so this is represented as this shape, silica sheet, and gibbsite sheet will be represented by this shape and the onward animation. Okay, so usually the clay will be made of those two types of the sheets. Okay, so first discussing the silica sheet. Silica is a tetrahedral sheet in which you will have one silica atom in the middle surrounded by 4 oxygen atoms on the side. Okay, So the oxygen atoms at the bottom will be shared. Okay, so you've got silica atom in the middle surrounded by 4 oxygen atoms over here. That's why it is called tetrahedral shape, because of the 4 corners which you can see over here. So the silica atom is in the middle. The oxygen atom at the bottom will be shared. Okay, they will be shared by the different molecules which you can see over here. Okay, so O2 over here is shared by this one and this one. These two silica is sharing this one. Similarly, this one is shared by these two, and this one is also shared by these two. While oxygen atom at the top carries -2 charge because it is not shared by any other atom. Okay, so if you calculate the net charge over here on silica sheet, that will be basically, because on the top there is a -2, then you have silica +4, okay, and then at the bottom you got 1, 2 and 3, okay, and each is shared, okay, with another silica. So it means -1 is shared by this one and -1 is shared by this one. So each silica is getting 1 -1 from the bottom. So 1, 2, 3, so 3 multiplied by -1, okay, so -2 +4, okay, and then -3, so -5 +4, and that gives you -1. So it means that the silica sheet is carrying a -1 negative charge, or it is a negatively charged sheet. All these atoms combined together, all these molecules combined together will give you the silica sheet. Now coming to gibbsite sheet, okay. In gibbsite sheet you have got octahedral sheet. It's an octahedral shape which you can see over here. 1, 2, 3, 4, 5, 6. 6 hydroxyl atoms on the sides. So that's why octa. And then there is aluminum atom in the middle, which is basically with positive charge. So if you combine several molecules together, that will basically form the gibbsite sheet. Okay. So in gibbsite sheet, now sometimes the aluminum is replaced with the magnesium, okay, which is called isomorphous substitution. Okay, we will discuss about silica sheet isomorphous substitution as well later on. So if you have the atom of same size replaced with another atom, okay, in a molecule, then that will be called as isomorphous substitution. Okay, so sometimes aluminum, instead of aluminum you get magnesium, okay, so that is called isomorphous substitution. So the gibbsite sheet either will have aluminum or magnesium, okay, and if instead of aluminum you got magnesium, that will give you a different types of mineral, okay, with different properties, with different physical properties. That's why I say that there are various types of the clays, okay. So now what happens is that the silica sheet combined with gibbsite sheet give you one element, okay, and several elements, several minerals combined together will give you the type of soil, okay. So first discussing the kaolinite, okay, how the kaolinite atom looks like, how the kaolinite molecule looks like. So in kaolinite you've got gibbsite sheet, silica sheet, gibbsite and silica, they forming the unit like this, okay. So over here you can see that gibbsite being positively charged is connected to silica sheet, so there is stronger bond over here, okay, and the size of the molecule, the size of the one element is very small over here, which is 7 angstrom, okay, as I discussed earlier. So over here 1 angstrom is basically equal to 10 to the power -10 meter. So it means that if you have 1 meter divided into 10 to the power -10 parts, okay, then 1 part will be basically equal to 1 angstrom, okay, or in 1 meter you got 10 to the power 10 angstroms, or if you put 10 zeros with 1, that many angstroms will be there in 1 meter. So 1 angstrom is very small size, which you can see over here, okay. So you will not be able to visually see this if you look at the clay, okay. So over here silica is connected with the gibbsite directly, you can see, and this is why it is called 1:1 mineral. So 1 silica and 1 gibbsite, okay, and several molecules combined together, several sheets combined together will give you the kaolinite, okay. In kaolinite you got hydrogen bond, okay, So what is basically hydrogen bond? On one side you got hydroxyl ion of your gibbsite sheet, and that is basically connected to oxygen ion of the silica sheet. Okay, so hydroxyl ion OH, okay, of gibbsite sheet. If you remember, on gibbsite sheet we've got OH on all the sides, and on the silica sheet we have got oxygen on all the sides. So this oxygen atom is shared with this hydrogen atom, basically making a hydrogen bond, which is stronger bond. Okay, so that's why, because of this tighter bond over here, this is a stronger bond, and the silica and gibbsite sheets are strongly connected to each other, and water cannot easily enter, which means that you get little expansion in this kind of soil. And this is less active mineral, which means it is more stable, okay, compared to the other types of clay. Then discussing Montmorillite. Okay, so what is in Montmorillite, what is the structure of Montmorillite? And Montmorillite is 2:1 or 2:1 mineral. Okay, and the size of single molecule is 10 angstrom, which you can see over here, is 2:1 mineral. So silica, two silica sheets are basically on the sides, and then there are gibbsite sheet in the middle. Now over here silica sheet is connected to silica sheet, and because there is no other connecting mineral in the middle, so that's why there is less bond over here, and water can easily enter. So it means that Montmorillite, they are basically more susceptible to water. In these there are van der Waals forces. Because of the van der Waals forces, they can attract more water. Okay, because of the more water, Montmorillite, they are more plastic, they cause more swelling and more shrinkage, so they are not good for construction. Okay, because there are van der Waals bonds in the middle, so that's why water molecule which is positively charged get easily attracted, okay, to negatively charged silica sheet over here. So between the molecule there is a water, here you can see, so water can accommodate over here between the two sheets. Okay, and that basically allows the Montmorillite to have high volume change, more swelling. Okay, and if then it is dried, then it will cause more shrinkage as well. Okay, so that's why Montmorillite is usually excessively swelling, and that's why it is dangerous for the buildings as well, because it can settle and shrink very quickly. Then coming to Illite. Okay, now Illite is also 2:1 bond. Okay, there are two silica sheets and one gibbsite sheets. Okay, the silica sheets on the side and gibbsite sheet in the middle. Over here there is isomorphous substitution. Okay, so silica is replaced by aluminum over here. Okay, so because of this, potassium is attracted between the two silica sheets, and potassium ions basically join the two silica sheets together, and that repels water. Okay, because potassium is provided with the positive charge over here to the negatively charged silica sheet, so that's why it will basically have no longer negative charge, so it will not attract water, and there will be stronger bond. Okay, so water cannot easily enter inside, because this potassium bond is stronger than the van der Waals forces bond and Montmorillite compared to Montmorillite. So that's why for swelling is the ability of soil to swell, to increase volume when you add water into that particular soil. So swelling ability of kaolinite will be the smallest. Okay, there will be less volume change, it will not contract or expand too much. Then you will have Illite. Illite will have slightly more swelling ability. Okay, swelling, if you put water into this soil, it will swell, it will increase in volume slightly greater than kaolinite. And then Montmorillite will have most of the swelling. Okay, it will have very high swell potential, Montmorillite. Okay, and kaolinite will have very less swell potential. So in kaolinite you will have less volume changes, and Montmorillite you will have more volume changes. Okay, so the Illite will be basically having least of the swelling over here, as I discussed earlier, and Montmorillite will have the greatest amount of swelling. Okay, so now moving on. So after discussing these three mineral types of the clay, you should always know that whenever the clay is present in a particular soil, it will greatly influence the engineering properties of that soil as a whole. Okay, because when moisture is present, the engineering behavior of soil will change greatly, the clay soil, okay, because of a clay mineral content issue. So for practical purposes, when the clay content is about 50% or more, then we should consider that soil to be primarily is a clay soil. For example, you can see a granular soil having clay, but you can see over here there is a lot of clay over here, and there is gravel as well. The gravel is a stronger material compared to clay, but here you can see that the clay is about 50% almost over here. If you do CV analysis, then you will get the exact amount of the clay. But if the clay content is even up to 50% in a particular soil, then we will have to consider that soil as totally its behavior like a clay, and we will have to, because the clay behavior is problematic. It can basically the clay can expand and contract upon wetting and drying, and its shear strength is very poor as well, which can result into failure as well. So that's why we'll have to be careful, and wherever there is a clay, we need to basically identify it and design our structure according to it. Okay, so this is the end of chapter number 2. In next class we will be discussing the specific gravity and sieve analysis, okay, and particle size distribution, determination of the various types of soil. So that is end for the chapter number 2. The handouts and the videos along with the PDF will be uploaded to the portal where you can check it. Thank you very much for listening.